Hi friends, welcome back. The next topic on our discussion is about demand paging. In a traditional paging system, the entire process is loaded onto the memory before execution. So if a process consists of n number of pages, then all the n pages are loaded onto the memory before we begin execution. But this is going to make a lot of wastage. This wastage, one, maybe that some part of the code may never be used at all, because there may be some conditional branches and all that, and because of these conditional branches and for that particular instant the branching conditions may not be favorable for some part of the code, and hence that part of the code may never run at all. Though it is not useful, it is unnecessarily using our memory, occupying the memory and wasting it. So that's one big problem with a traditional paging system. So the solution for this problem is demand paging. It's a smarter approach. So here, instead of loading the whole code onto the main memory, we can load only the pages that are currently required. So one thing is very clear, that any given time a processor can work with one instruction, and that one instruction definitely will be part of only one page. That means, logically speaking, any given time, if we had one page on the memory, that is sufficient. But it's not necessary that all the processing is done instruction by instruction in the same sequence. There may be the jump statements, conditional jump statements and all that, because of which the control will be shifting from one page to other page and all that. So therefore it is logical that we may better have more than one page on the main memory, so that even these jumps and all that are taken care. So with this, what happens is, now we don't need entire space to store the program onto the main memory. A small space is sufficient. So the number of pages that are currently in use only can be allocated a memory, and the rest of them can be put on the back end. So that's what the concept of demand paging is. And whenever a process tries to access a page that is not on the main memory, then of course something should happen, and that what happens is called a page fault. A page fault occurs saying that such page does not exist on the memory. So we need to get that page onto the memory. So before getting that page onto the memory, some page has to be moved out from the memory. So one moves out, other comes in. So in and out activity has to happen, and this is done by the operating system. So the operating system brings the page from the secondary storage onto the main memory, and before getting that new page onto the main memory, one of the pages has to be moved out back to the secondary memory. So the key points of demand paging, the first thing is what we call lazy loading. That means all the pages are not required at any given time. So whatever page is required, only that one will be loaded. All others are not loaded in advance, so only the one which is required will be loaded. So others we have showing some sort of latency, laziness and all that. And we have something called page fault. Whenever a page is referred that is not on the memory, then a siren is ring, and this informs the operating system, says that the page we wanted is not on the main memory. Please do something, get that from the secondary memory, put it on the main memory, so that the process can continue its execution. Then we have a valid invalid bit, that is the page table. How do I know whether such a page exists or not in the main memory? So in the page table, we have one bit result for that, whether it's going to tell us whether such page exists on the main memory or not. So that's a valid invalid bit. And if the page is in the memory, then we make it valid, and if it is not there on the main memory, then it's invalid. So the advantage of using demand paging is it saves a lot of memory, allows running larger programs than the available physical RAM. So the physical RAM, or any time the RAM allocated for a process, may be very small compared to the real size of the actual program. Then in in spite of not having sufficient memory, we can still make sure to run the whole bigger process in a smaller available memory. That's the advantage of working with demand paging. Yes, of course, nothing comes free. There is disadvantage also, that every time there is a page fault, then this transfer of a page from main memory back to secondary memory, and the new page from secondary memory to the main memory has to happen. And this is an uh, it's an extra work, and that's not going to be counted as the work done. So it's an overload, and because of this, what we can say is the performance slows down, and this overhead definitely is going to degrade the performance. And if it is not managed properly, then even it may crash. So the analogy, get like a large textbook in a library. Instead of carrying the whole heavy book to your home, you can just photocopy the pages you actually need and use them. And later, if you need any other page, then you can go back and then again get another copy of that and continue. So this saves a lot of efforts to carry the whole book. So the whole book may not be required any given time, so only a part of that is required any given time. Just make a photocopy of that and use it. So that's a simple analogy we can talk of. So this figure shows that a program A is there, and there is a program B we wanted. So whenever we want new pages, then some old pages have to be swapped out and new pages will be swapped in. And this process is an overhead and going to degrade the efficiency, the performance of a system. Now here is an example. Our example consists of 8 logical pages, A to H, and out of which A, C and F, only 3 are there on the main memory. Out of A, B, C, D, E, F, G, H, only 3 get the chance to be on the main memory. And it says that A, that is the logical page 0, A is there on the frame 4. So frame 4 we have A, and then we have C. C means the logical page number 2, it is there in frame 6, and F we have, which is there in frame 9. F is logical page 5. 5 has got a address of 9. So 4, 6 and 9, 4 is A, 6 is C, and 9 is F. Only 3 are there for this particular process, therefore only 3 pages are on the main memory. So only for 3 pages we say V, and others we say I. This is the valid invalid bit. So when we are working with the execution, say currently some instruction in page A is being executed, and there we encounter some jump instruction, conditional jump instruction or something, and if it happens to be in page C, then there won't be any problem. It says go to page C, then look for page C. Page C is in the logical page number 2. So in logical page number 2, it is valid, and where it is in the frame number 6. So go to frame number 6, and you know displacement, go to that particular line and start execution or continue execution and so on. Now instead of going to see if it asks to go to a location which is there in page B, Then page B is logical page 1. In logical page 1 says I, the bit says I, that means invalid. It means that page B is not there on the main memory. So we have to get page B on the main memory. So for that, operating system raises an alarm, says page fault, and we want page B onto the main memory. If only these three are the page frames allocated for this particular process, then to get page B, either A or C or F have to be moved out. And if these are being modified, then the latest copy of that has to be saved onto the backend. Otherwise, if they are non-modifiable, then we don't have any problem. Say if we want to move out F, in place of F we want to get B, then F is replaced with B. So B comes here at frame number 9, and this invalid bit will become valid, and F is no more existing. F is location 5, and here it was 9. Then we said blank and we call it invalid. But make sure that the contents of F were same as the contents of F here in the backend. If they are not same, then this copy has to be written back onto the secondary memory, so that next time if page F is required again, then it will be swapped in. So the process of getting B in this place is called swap in, and the process of moving F out back to the secondary is called swap out. So this process, swap in swap out, is done continuously, and if the page faults are more, then it is going to degrade our system performance. So we need some best way to make sure that the pages are selected such that these pages which are swapped out are selected such that any given time minimum page faults occur and all that. So that is the concern we have when we are deciding with this demand paging. So that's it for now. More details to continue. Thank you.